All right, welcome back there, function folks. It's finally the end. This is the last day of new stuff. Now we have still a test to do and some review videos and that little matter of the exam that we want to take care of. But here we go. The 3-minute review, and please stop this and try it yourself. This is kind of like a easy thinking question where you just have to identify each of the function types, basic function types that we've done this year or in previous years, and think about what situations they model. So you should try this if you haven't. I'm going to take it up right now. So pause if you haven't tried it on your own. Here we go. There are my answers. What I want to mention, and these are pretty close to standard answers. There's some that kind of overlap a bit. We don't know what happens on some of these. For instance, on the part of the graph that's cut off, maybe this quadratic starts going back up, or maybe it's just a chunk of a sine wave or whatever. But for the most part, those are the answers. What's interesting here, and I'm not going to go through all of these, but it says dream up a situation that could be modeled by each graph. What would the dependent and independent and dependent variables be? Well, this is a favorite thinking question of mine, and through the years, like this is a grade 9 question, grade 10, grade 11, we were introduced to these, and then this one showed up this year, this one was this year, this one was this year, exponential decay. The downhill one was last year, but again this year, of course. This is one of my favorite ones to try and try and ask people come up with a situation. Well, what would be rational, and what's the variable here to make a rational equation? I like this one. Number of workers and time to complete a job. Think of like a construction site or something like that. So as you add workers, the time to complete the job is going to go down. But even if you have an infinite number of workers, it's still going to take a little bit of time. It'll never be zero. Similarly, when the number of workers is zero, what time is it going to take to complete that job? Well, it's never going to get done. As x goes to zero, the number of workers goes to infinity. Of course, this should be dots, right? Should be actually integers, but that's not allowed here. Uh, Other ones, typical ones, would be like a ball being fired off of a cliff or something like that, where this is time and this is height, or this is horizontal distance and this is height. Lots of different. We actually did a whole assignment on sine and cosine functions. Cubic polynomial. It's hard to find data that is modeled nicely by a cubic polynomial, but it might be something like if this is like a stock price or something like that. Oh, this is stock price here, rather. Stock price, and this might be over some sort of time frame where that's time, where it goes up for a little bit and then down and then back up. But of course, if yours makes sense, you stick with your ideas, right? Because if you want to ask whether you're right or not, don't be afraid to ask about that in class. Now, in class, next day, we're going to have a little in-class activity, quick, before you get into the homework for today, and it's got to do with these cards. So look for these cards. That's the in-class activity. I'm going to skip over that, and you'll be able to take this up in class. This is, again, a bunch of situations, and you match them with what their graph would be. Similar to this idea, but a little bit of matching activity. In the note here, this is modeling day 2, is essentially what do we do with when we're just given data. And we've ran across this animal earlier in the year. We did some of this in the trig section, and again in the exponential section, and all over the time. So a bunch of data, and I mean, with the numbers being crazy like this is time, and CFS, it says, is cubic feet per second. CMS is cubic meters per second. So the raging river hourly discharge. So this must be something, they're measuring the amount of of water that's going through some sort of system, and I got no idea how it would be even changing, but this is some data that somebody has collected at some point. The US GS, I don't know what GS stands for, it doesn't matter, we have data. The question is, when we have all these functions to choose from, what function do we choose? Which type of graph is it? How would we ever know what to do? Probably most people are thinking I'm going to use regression because that's a lot of numbers to work with, but how do I know which one? Well, this is what we're talking about. So first of all, what's the technique? Probably. We need a picture, right? We need to plot the data either by pencil and paper or technology. And we saw again and again this year that when we're given data, it's almost easier to type it in to either graphing calculator or a spreadsheet or Desmos when it's a whole bunch of data like this. And the data management people, MHF4U, you are good at this, right? This is that whole two variable statistic stuff. When we plot the data, then look at the shape. Usually it matches one of our basic shapes, and then we're going to do that regression, linear regression, quadratic regression, sinusoidal regression, or whatever, right? That'll be what we do. Look at the shape, then use the appropriate regression. And essentially, that's what we're going to do. So plotting the data, I don't know if I included this graph in your package, but that's what it looks like there. So which picture does it look like? Starts going down quickly at first and then more slowly, and there's nothing else. It looks like there's going to be an asymptote here. This is probably exponential decay, right? Probably exponential decay. It's this picture. Pretty close anyway. And so that means when we choose regression, we're going to do some sort of exponential model. And I'm going to do that. I actually did it in Desmos. So I'll show you what I did in Desmos. I had all this data in a spreadsheet, wherever I found it, spreadsheet, there it is. And believe it or not, I just copied that, pasted it into Desmos, and I got almost that same graph. Now, how do I actually, get the regression equation in Desmos? Well, I have to know which model it actually is, right? So this is, I think when I pasted it, it made it x2 and y2. You see that, x2 and y2. And so if I wanted an exponential graph, I'd put in an exponential equation. I went y2, and then that little swoopy symbol, the tilde, and then I'm going to put in an exponential graph. So a times b to the exponent x2, exponential graph. And notice this one isn't actually that great of a model. For some reason, I think Desmos actually grabs only a few points. There's no way that it shouldn't be able to grab, do a better graph of this, but at least it gives me something that I can work with. So there's my function, and I'm just going to write that down. 2530 is my a value back in the lesson here. So from Desmos. And then my base value was, what was it? Where is it? There it is. My base value was 0.959. And there's my function. Now, what happens is you say, well, okay, this is exponential. I can see it's exponential decay. It doesn't look like a great graph, though. It misses a lot of points. And like I said before, I think Desmos kind of does a strange job with its exponential regression. But what happens if I tried a different one? Maybe I try a linear model. Y2 tilde, and then I'm going to write M x2 plus b. Well, there's a linear model. Maybe the linear model is just as good. How do I tell? Well, one thing about this is this R value called the correlation coefficient, not real important for us, but important for the data management people. And this tells us, and we can tell from the picture, that the green graph doesn't fit as good as the blue graph. But how close this thing is to 1 is a good indication of how good the data fits. So I'm going to write that in there. Negative 38.8 and 240 is my linear model. Negative 38.8x plus 2040 is my linear model, but not as good. Here, my r squared value is 0.99. My r value here was 0.94. If I take the square root of 0.99, that's actually going to give me a better value. And I'm just doing that here on a separate calculator to give me 0.995. Right? So I just took the square root of 0.99. R is 0.995, which tells me that this is a better model since it's so much closer to 1. Dandy. Okay, so we're using technology. And is there any way we could have actually done this using my skills from exponential function analysis or trig function analysis? And the answer is absolutely. How would have we done that? Well, I could have had my starting time as minute 1 minute after midnight or whatever, 1 minute after, or hours hours after 1 o'clock here, and then my starting value, my C value, could have been 2410, and then for my A value, my base, well, I could just find these ratios, right? I just go that divided by that, that's 0.992, that divided by that, and I got all these calculated beforehand. Let me just look them up here. And we talked about this earlier. Then all I would have to do is then find the mean of these possible R values. That's kind of hard to read. This one is 0.950, and this one is, when I do this ratio, is 0.965. And remember, I have to do that for all of them. It would be better if I use a spreadsheet. If I wanted to find the average base, the average ratio, then I'd multiply all these up and take the root, right? So that times 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 that, and I take the root, and then I could get my own model, right? Maybe this is, maybe this value, say it would be a little bit different. Let's say it's 0.63 or something like that, and then I could graph my own. This is my own, what I'll call the logic model. And it's not always I can do this logic model because I don't know, I don't have the skills to model this stuff. But this one, yeah, maybe I could. And that is up to you. Completely up to you. The next example, I think, is even more fun. But the next example, which is model the height of the dampened spring. The dampened spring I show you in the, I guess I'll call it part 2, about what the dampened spring is, and then we'll analyze that data in part 3 coming up.